All right, so this is my Lab 5, the Do Anything You Want lab for Physics 2211, and I'm Ruhun De Silva. So basically, I did this on the Slinky, and just a brief introduction. We're going to be using Newton's second law, the momentum principle, which basically states that a system's change of momentum is proportional to a net force. And then we also have the gravitational force, which is a constant of 9.8 meters per second squared. And then you also have the drag force, which is non-constant, and it's equal to the proportionality constant times the current velocity squared. So we're mainly going to use two equations. This is the position update formulas and the velocity update formulas. And the initial mass of the Slinky is 0.22 kilograms, and the initial y velocity is going to be 0. So the purpose of this lab is to use the skills and resources that we have gained and used so far in this course, and we're going to apply these to a problem we designed, and then we're basically just going to show mastery of these prior topics to show what we've learned. And overview, we're going to observe the motion of a falling slinky and track its position with the tracker software, and create a computation model of the scenario using Python to compare the results. And the final result is at the bottom there, which says that the slinky is going to remain stationary until the top hits the bottom of the slinky. Okay, so for the experimental part, I labeled the system being the slinky in the Earth surroundings, with the air being the surroundings. Like I said, the mass is 0.22 kilograms, the initial velocity is 0 meters per second, and the initial stretch length is 0.122 meters. Basically just tracker position. Slinky doesn't move, as you can see here. The bottom stays in the same place, whereas the top is keeping on falling. Yes, so then for the computational model, we use the initial value, the initial measurements that we just used, and we're also using Newton's second law and the velocity and position update formulas. Yeah, and basically just everything that we said before. I'm setting up the gravity, the tension force in static and equilibrium, and the net force of gravity and drag. So yeah, so this is the computational model that I used. And for comparing data, you can see the computational and real model right here. As you can see, they are very similar. Therefore, I got all my values right in my computational model. So yeah. So for the discussion, so what does it mean? As I said before, the forces in the y direction cancel out, although we do have the gravitational force acting downward on the slinky. The slinky acts as a big string and counteracts the force with tension, force that's equal and opposite. So basically, the bottom is going to have a net force of 0, therefore, it will remain stationary. And in conclusion, there are some sources of error. First being external forces that we may not have accounted for. And also maybe some human error, whether that be with the tracker, the initial velocities, dropping the slinky. Yeah, those are sources of error. And in general, this lab has talked about Newton's second law, gravitational force, and drag force. And yeah, thank you very much for listening. That was my lab 5 on do anything you want.